Hello, friends. This is Sayeda Tahira, and I am an electrical engineer by professional degree and a teacher by around 7 years of teaching experience. And I'm from Pakistan. So, today I'm going to talk about, I'm not going to disclose it. Let's see what I'm going to talk about. A very, very interesting topic from mathematics. Okay, so I am going to open up my notepad first, very quickly introducing a great topic from maths. Okay, guys, let's have a velocity time graph, okay? And this is the speed of my vehicle, right? So, the distance traveled by that vehicle is going to be v times t, okay? If I focus on this graph, I can just see that the shape of this graph is just like a rectangle. And I know that the area of rectangle is length times width, and in this case, it's going to be v times t. Okay, which means for the velocity time graphs, the area under the graph is going to give me what? Distance. Hmm. Okay, let's have another type of graph with me. Suppose my vehicle's journey was modeled as this kind of graph. Okay, if I just use the same fact I have just observed, that the area under the graph, okay, the VT graph, is going to give me the distance traveled. And if I focus on the shape of this graph, which is a right angle triangle, and I know that the area is going to be half base times height per triangle. And in this case, it's going to be half t times v, or half v times t. And this area is definitely going to represent the distance traveled by my vehicle. Makes sense? So it means it's quite interesting to know the areas under the graphs. As in this case of the VT graphs, they are representing the distances traveled by the vehicles. And if it is some other category of variables plotted together, they may be representing some other quantity in physics. Anyhow, area under the graph is of high importance. Okay, moving on. Let's have another type of a graph. That's again a VT graph. Suppose it's a curve now. Again, I am going to use the same fact that area under this graph is going to represent the distance traveled by my curve, or my vehicle, I'm sorry. So what should I do now? How can I find out the area under this graph? One way is, which the mathematicians mentioned to us, is that I can just split up this region into the rectangles of similar widths, okay? And then finding out the areas of these rectangles and adding them all may give me the area under the curve. But that's not the total actual area. That is just an approximation. How? Let me show you. Areas represented by these rectangles are marked as these green lines. I am not able to cover up this part, this region under the curve, right? Which means, yeah, I would be able to get the distance or the area under the graph using this approximation strategy, but that's not the actual distance, right? But what if I increase these number of rectangles? Let's say their number raises to infinite, so many rectangles, and their width. See, this gap is minimized. That gap is approaching zero. In imagination, if I am splitting the region under this graph into so many rectangles, such that the width of those rectangles is very, very small, I would be able to reduce this gap or this lost area, and I'll be able to approach the more realistic actual value of the area under that graph. In other words, I'll be able to reach the actual distance traveled by my vehicle. Okay. Now, the case is, it's really high time in our discussion that if I have, in my imagination, if I have infinite number of rectangles, how can I find out their areas and add them all? It's again a big task, right? And here we go to accumulate the areas of those so many rectangles of very, very, very small widths. I have an operator in mathematics, and that is really cute operator. You might have seen it many times. It is called integral operator, or the process it follows to find out the areas of these mini rectangles is called integration. Even in English language, we use the word integrated curriculum, for example. Integrate means adding on all the mini areas together. Okay, so here we go. I was not disclosing the topic to you. The topic today we're going to talk about is integration. Okay, and a very important application of this integral operator or this process of integration is to find the areas under the curves of any shape, right? And we know that, for example, in the case of the VT graphs, these areas were representing what? They were representing the distances traveled by your vehicle. And in many other cases, for example, if I have a curve represented by the function, let's say x squared plus 2x minus 9, for example, finding out the area under this curve might be of interest to me if even if I know what type of physical quantity this area is going to represent, maybe if I do not know at the moment, but this is a fact that finding out the areas under the graphs is of very high importance, right? And how I can do that, I'm again stressing upon the fact that this operator, the integral operator, is going to do that miracle for me. It will be splitting out my region under the graph into so many mini rectangles with a very, very small gaps. And it would be just adding on all of them, giving me the a result as close as possible to the actual value. Is that okay? With this, I am going to conclude my today's lecture, today's discussion, at a very happy ending note that integral operator is really, really important, impactful to find out the areas under the graphs and why these areas under the graphs are of high importance to us, right? So in the next video, I'm going to talk about how this integral operator works and how it assists us in finding out the areas of the graphs even without plotting them. Okay, so stay tuned. This is Sayeda Tahira. I'm going to meet you in the next video. Thank you so much.